Hello, my name is Aurélien Renaud, and I'm going to present you on the behalf of my colleague Alexis Mondu, Antoine Cornejo, and Vincent Lemaire our work entitled Early Classification of Time Series, a Survey and Benchmark. So we are interested in early classification of time series. The goal here is given a partially observed time series to predict its associated label y at time hat t, the smallest one possible, supposedly, before deadline big T, which we know beforehand. So the whole point of the task is to account for a trade-off between how early and how accurate our predictions are. This kind of trade-off is characterized by two types of costs. The first one being the misclassification costs, which corresponds to the cost we pay when predicting the wrong class, basically a matrix. The second one is the delay cost, which is usually an increasing function of time. So the goal is to minimize the sum of these two costs that generally evolve on opposite direction, and which correspond to the empirical risk. So there's many ways one can implement ECTS algorithm. One popular way is said to be the separable framework. Separable because within this framework, the classification module is implemented separately from the triggering one. This setup is quite nice since it allows you to perform easily a whole bunch of ablation studies. It's modular. You can clearly assess each component's contribution to performances. So you can typically compare trigger function, keeping the classification part fixed, or the other way around. It works as well. And you could also leverage any kind of off-the-shelf time series classification algorithm, which is nice. So you could also solve the two subtasks jointly using a end-to-end framework. This is usually done using deep learning architecture in the literature, but in this paper, our main focus remains on the separable methods, which represents the major part of state-of-the-art. So we are proposing this taxonomy for the separable SCTS. Not much to say about classification part, except that as long as you have a model that can output any kind of prediction based on a varying size time series, you're good. Concerning the trigger function, we propose three main properties, which are non-mutually exclusive. So that means that any trigger function could be, well, all of them all at once, or on the contrary, none of them at all. First one of which being whether or not the model is cost-informed. So that means whether or not it can take as input any kind of cost function. More specifically, within the cost-informed method, some trigger models can, in addition, adapt to changes in cost during testing time. So that's the case, for example, in the economy framework, which explicitly computes some kind of cost expectation for every future time step. And so it can thus adapt to changes in the cost function during testing time. And this is a nice property in the case, for example, where the costs have been misspecified in the first place. The second property is whether or not the model is confidence-based. So that means whether the trigger model ground its decision based on some kind of metric, reflecting how confident the classifier is in its prediction. So you can whether be instant-based, only accounting for the last time step, or sequence-based if you're considering the whole sequence of past time step. So one of the simplest method of this kind one could think of would simply consist in monitoring the maximum probability outputted by the classifier and to learn some threshold to be applied over it, such that when the probability exceeds this threshold, it triggers a decision. And well, we'll see later in the experiments that those kind of baseline is actually rather hard to beat. And the last property is the anticipation-based property, also called non-myopic. And well, it basically means that those kind of models leverage any kind of costs. Could be forecast of the type series itself, of the costs associated to the series. That's the case for the Calimero approach, for example, which tried directly to regress the difference between the best cost what can reach between next time step until big T, deadline big T, and the cost we are paying right now. So this kind of regret measure. The same idea, reinforcement learning based method that are also trying to minimize regret could also be considered as anticipation based approach, as they are estimating some kind of expectation of costs um, between current timestamp and until the end of the episode. So the big deadline, big T in our case. So we can see that the state-of-the-art approaches are populating our taxonomy quite nicely. And so having said that, how can we evaluate those kind of ECTS method? Well, the evaluation matrix, once again, is the average cost, the empirical risks. We are adding a weighting parameter alpha, which account for a balance between the misclassification costs and the delay costs. So alpha near to zero means that you only account for the temporal costs, while alpha near to one means you only account for the misclassification cost. So in this paper, we are testing out two types of different cost setting. The first one is the binary balanced misclassification costs alongside a linear delay cost, which is the most widely used cost setting, the one you can find in pretty much all the paper the literature to date. And we propose another one, which tries to mimic some kind of anomaly detection setup with a unbalanced misclassification costs, in which like minority class is way more costly than the other ones, alongside a temporal delay costs that has a exponential shape. So another matter of interest when doing SATS, ECTS experiments is to the data sets over which we are applying our methods. So specifically, we are proposing a new benchmark of 34 data sets that are respecting two main properties. The first one being that, well, all the data sets should display some kind of information gain over time. So, for example, in the figure, you see a free class problem in which like every class has a discriminative signal within a third of the series. And well, while the first class is easily distinguishable from the early part of the series, the two other has to at least wait for half of the series or so to be separate from one another. So it basically means that you should observe some kind of useful information for the classification task while collecting new data points. Otherwise, there would be no point in applying ECTS algorithm at all. The second point is that your data shouldn't be normalized series-wise. That is, with the complete series knowledge, as well. This setup, first of all, is not applicable in practice, but it could also introduce some kind of temporal leakage. Imagine like if your class depends directly on the series variance, you could like normalizing it, introduce some kind of information about the series class in the early part of the series, undesirably. So we propose this new benchmark that is respecting the properties, in which you can find both binary and multi-class problems. So the goal here is in those experiments to compare trigger models while keeping the classification part fixed. So for the classifier, we have chosen the mini cat algorithm, which is one of the best performing time series classification algorithm. The 9 trigger models we have tested have been re-implemented, and you can find them in the open source Python library here. And we also had like 3 simple baselines to our comparisons, 2 of which are extremely naive, which simply consist in triggering decisions at first time step or at last time step always. And a third one, which is the single threshold method I just mentioned earlier, which simply consists in like researching a threshold to be applied over the maximum probability estimated by the classifier. So in the linear and balanced cost setting, if we are analyzing those kind of plots representing the mean ranks, well, we see that uh, surprisingly, there's a whole range of alpha values for which like there's no better strategy than just to trigger the decision instantly. So that's the two baseline in bright red. And well, more specifically, we can see that the single threshold baseline in brown, the broad curve, is actually highly competitive all the way through. So the question here is whether or not is there any point in developing more complex methods, since well, a single threshold seems to work just fine. Well, and the answer is yes. And I encourage you to go to read the paper to know the end of the story, specifically to see the results about the second class setting. There's a whole bunch of ablation studies about classification part, about calibration, about normalization also. And well, if you have any question, please feel free to reach out at this address. And well, thank you for listening to the video.